First, we are going to put in context the paper by defining what is a safety case. A safety case is a logical, convincing, and well-structured document that uses multiple pieces of evidence to support the claim that a system is acceptably safe. It can be represented in three different forms. In our case, we are going to be interested to a type of graphical representation known as goal structural notation, or GSN. As you see in the graph, we have 9 elements. The first is a goal. A goal is the claim to prove about the system. A strategy is a description of how to realize a goal. The composition, it always appears between parent and child goals. A context is a reference to contextual information or a statement of contextual information. It can be related to a goal, a solution, or to a strategy. A solution is the available source of information to directly support a goal. A justification is the statement or description that provides the rationale behind the adoption of some strategy or the presentation of some goals. And assumptions are additional information linked to a goal or strategy, which is sometimes necessary for the goal decomposition. We have also two types of arrow. An arrow linking between goals and strategy, or goals and solution. It describes the relation supported by. The second type of arrow linked between a strategy, a goal, or a solution, and the context. It represents the relation in context of. However, in goal structuring notation, we cannot show the degree of confidence or uncertainty in many aspects of the argument structure. For instance, in this example, we can estimate the degree of confidence being in the goal G1 or in the solution SN1. The same goes on all the components of goal structuring notation. To address this issue, we fixed 3 objectives. The first is to quantify confidence degree by using belief function theory, which is more appropriate than a standard probability theory used, for example, in a belief Bayesian network. The second objective is to extract and analyze the methods of propagation of confidence proposed in the articles that we have selected. And the final objective is to suggest a method of propagation based on our analysis. Now we are going to introduce the belief function theory, known also as Dempster-Scheffer theory. This theory is a generalization of probability theory that takes into account both aleatory and epistemic uncertainties. For the case of probabilities, this theory takes into account only the aleatory aspect. And Dempster-Scheffer theory is a powerful tool to deal with incomplete information. Now we are going to define 2 tools used in this theory. The first is a mass function. A mass function is the equivalent to probabilities in the probability theory. It's a mapping of the power set omega, known as frame of discernment, to a closed interval between 0 and 1, and like the probabilities, the summation of the mass of omega are equal to 1. The mass of the empty set are equal to 0, and we call the focal set all the positive masses of omega. Here we give a little example of a statement A saying that a clock provides the right time. The frame of discernment is made of 2 states, true and false, and the power set is made of omega is made of 4 elements: true, false, the empty set, and the universe omega. Here we are going to define the belief function. A belief function represents the summation of all masses that support the statement A, and in the same way this belief function represents the summation of all masses that support the negation of the statement, and we can deduce the uncertainty function by using belief and disbelief functions. We take again the same example in the slide before. Belief on A represents the fact that the clock provides the right time. Disbelief on A represents the fact that the clock does not provide the right time, and the uncertainty on A represents the fact that we know nothing. To assess confidence in goal structural notation using the Dempster-Schiffer theory, we introduced two parameters: confidence in premise denoted MP and confidence in the rules denoted MR. We start with confidence in premise. Let's take A as a statement with a frame of discernment made of two states, and A and A bar, and a mass function MP with three measures. An opinion about the statement A is assessed with three related measures: belief, disbelief, and uncertainty, and we can formally define the confidence in premise by the three equations below. Before talking about the confidence in rule, we are defining two elements. We are going to define two elements. An argument types define the relation between premise and the conclusion, and when we transform this argument type, generally defined in an informal way, to a formal definition, we talk about a rule. In the example below, we have a conclusion supported by one premise. The argument types is defined by the expression: if the premise is true, then the conclusion C is also true. Formally, we can formally define this expression to P implies C, and the two equations below represents the belief degree on the rule. Now we are going to present the assessment process. First, we define the relationship between premises and the conclusion and transform them to a usable form, which is rule. In the second step, we choose the mass assignment to each focal set. And in the third step, we choose the appropriate aggregation rule based on the situation described in the argument type. For example, if we have a conflict. The complete process includes a fourth step consisting in transforming expert opinion to belief degree. However, this aspect will be not addressed in this presentation and in the article. Here we are presenting the three articles that we selected for this study based on their use of Dempster-Schiffer theory and goal structural notation. They present several argument types and use many aggregation that we are going to use as well. In this table, we transform all the argument type present in the previous article and express with informal way to a formal language and group together those that follows the same rules. For example, with type 1, we have the argument type was named necessary and sufficient conclusion argument. In the second article, this type was named consensus rule, and in the third article, this type was named full complementary argument. We can notice from this table that we have two groups of argument types. Argument with conjunction and equivalence in type 2 and type 3 and type 2, and conjunction with implication in type 3 and type 4. For those who notice that type 5 use disjunction with implication, notice that type 5 is logically equivalent to a type 4. In this slide we are going to talk about the choice of logical connective, starting with the implication logic connector. This connector can only indicate that the system is safe. It cannot prove that the system is faulty, and the disbelief degree are equal to 0 in this case, because we cannot prove that the system is faulty. We assume in this case that implication is used to certify the safety of the system. The use of equivalence logic connector assume that we have a symmetry between premises and the conclusion, and the disbelief degree is different from 0 because the expression P is equal to C is also equivalent to P bar equivalent to C bar. In other words, it's include the expression when P is false, it's implied that C is also false. We assume that equivalence is used to evaluate the safety of the system, or when the symmetry between premises and the conclusion is verified. Now we are going to talk about the aggregation rule. The Dempster-Shafer theory offers many aggregation rules to calculate the joint mass of each premise or sub-goal to obtain the confidence in the top goal. We can group these rules in 3 categories. We have conjunctive rules, with the example of Dempster rule of combination. When the degree presented in the example below, when the degree of conflict is near to 1, the formula becomes unstable because we divide by a number close to 0. To address this issue, we have Jaeger's rule that we can use if we have an important conflict between premises. The second category is the disjunctive rule, with the example of consensus rule, and the final category is the cumulative rules, with, for example, the weight average rule. This rule can be used when we have to make make a trade-off between conjunctive and disjunctive rule. In this table, we present the consistency between arguments type and the combination rules used, and we notice that half of the used combination rules are inconsistent with their argument description. For example, in the third line, we have a argument or alternative argument. In this type, the authors use Jaeger's rule, but in their argument type description, we don't find any mention of the existence of a conflict between premises. Now we are going to talk about the choice of the mass assignment. This choice is very important because it has a huge impact on the final result. We have 2 ways to assign masses. The first is to assign one mass function for each premise, and the second is to assign one function between all the premises. In the example below, we have a conclusion supported by two arguments, P1 and P2. We can either use two different mass function or one function. In the first way, we can measure the uncertainty about each premise, and in the second way, we can differentiate between the uncertainty being in the first and in the second premise. Now we are going to our proposition. In our proposition, we choose to use only the argument that use conjunction and implication, because the goal of our study is to certify the argument structure. We are also going to use only Dempster-Scheffer theory, because in our argument types we don't mention the existence of conflicts between premises. And we are going to use both ways of mass assignment. To get our first formula, we use the type 4 with one mass function per premise, letting the belief of the conclusion, the eth conclusion, as the products of the belief in the premise and the belief on its appropriate rule. We can say that this expression is a multi-evaluated disjunction. It's enough that the confidence in the conclusion supported by one premise is equal to 1 for the confidence in the whole conclusion to be equal to 1 as well. In the second formula, we used the type 4 with one mass function distributed over all the premises. Here we can say that the confidence in premises is related, because if the confidence in one premise increase, the confidence in the other premises decrease. In the third formula, we use type 5, and remember that a type 5 is equivalent to type 4, and we use one mass function. The third formula is different from the previous formula, even if we use the same aggregation rule and the same argument type, because the mass assignment was different. And with the fourth formula, we use type 3 and one mass function. This expression represents a multi-evaluated conjunction, because if the confidence is equal to 0 in one one belief function of a premise, then the confidence in the whole conclusion becomes equal to 0. To summarize, in this presentation we introduced the safety cases and Dempster-Scheffer theory. We compared and analyzed 3 existing arguments type, and we proposed a methodology based on 4 criteria: arguments type definition, logic connective, mass assignment, and the aggregation rules. In future works, we are aiming to experimenting our approach in application with high uncertainties, use the transforming expert opinion into usable numerical values to complete the procedure, However, this process is very subjective and give an imprecise results. For that reasons, we are going also to developing a non-quantitative approaches. Thank you for your attention.